All right, welcome back to another week here. We're just going to be checking out chapter 12.1 this week. And actually, there's only going to be one homework problem for this week, and if you read the page already, you guys are never going to see chapter 12 on an exam, so you just got to get through the homework assignment and then spend your extra time either reviewing for the final or making sure that you're getting your final project done. All right. So we're going to go over the only problem you guys have to do from chapter 12, which is 12.1.1, which is, again, the only problem for homework number 16. Let me start by reading the problem statement here. Startup cell phone applications company is interested in determining whether the household incomes are different for subscribers to 4 different service providers. So 4 different service providers means that the number of populations that we're sampling from is going to be 4 different service providers. A random sample of 28 subscribers is taken from each of the 4 service providers. And annual household income for each subscriber was recorded. Partially completed ANOVA table for the analysis is below. And the first thing we want to do is just fill out this table. Now, first thing I want to mention is that this table and all of the definitions are on page 441 of your guys' textbook. You might want to take a look at that. All right, so all that they gave us were these 2 values in blue right here, which was the sum of squares between samples and the total sum of squares. So the first thing we want to do is calculate out the SSW, which is the sum of squares within the samples then. So the whole thing is that the sum of squares between and the sum of squares within has to equal the total sum of squares. So of course then the sum of squares between is going to be the total sum of squares, subtract out the between sum of squares. So we just take this 9,380,718,797, subtract out this 2,788,000 or 788,899,340. And you end up with a sum of squares within of 6,599,819,457. So just total, subtract out sum of squares between. Next thing we want to do is just identify the degrees of freedom for the samples, or between samples, within, and then total degrees of freedom. Now, for the number of degrees of freedom between samples, that's just the number of populations, subtract out 1. In this case, we had 4 populations, so that's just going to be 4 subtract 1, which is, of course, equal to 3. For the degrees of freedom within the samples, that is the sum of all the samples, subtract out the number of populations. Now, for the sum of all the samples, keep in mind, we took 4 samples of 28. So to get the total number of samples, that would just be 4 multiplied by 28. And then we have to subtract off the number of populations, which is, again, 4. And that comes out to be 108. Then finally, for the total number of degrees of freedom, it's again just the sum of all the samples, but instead of subtract out the number of populations, it's just subtract 1 in this case. So the same thing, the sum of all the samples would be 4 multiplied by 28, and then subtract 1, and you end up with 111 there. Now, the next thing we want to do is figure out the mean squared between and the mean squared within. So that's just the sum of squares between divided by the number of degrees of freedom there, and the sum of squares within divided by the number of degrees of freedom there. So let's see, sum of squares between is going to be this 2 billion, so on. So So sum of squares between divided by the degrees of freedom there, which was 3. And we get 929,633,113. Now, our mean squares within now is just sum of squares within, or this 6,591,000,000, then divided by those numbers, the degrees of freedom there, which we've already found out was 108. So that's going to be and divided by the degrees of freedom there, which was 108. And that comes out to be 61,035,000 or 35,365. Now finally, to figure out the F ratio, all that it is just the ratio, or you take the mean squared between divided by the mean squares within, and that's just going to be our 929 million there. Divided by our mean squares within, which is the 61 million. And we end up with an F value of 15.23. Alright, so when we actually want to test the hypothesis, which we'll do in just a second, that's really the only value that we're interested in, the F value. Alright, continuing on with this example here. This is just continued 12.1.1. In the last part, we filled out that ANOVA table, and we found out that our F test statistic was 15.23. Now what we're going to do is we're actually going to perform a hypothesis test, and it asks us, based on the sample results, can the startup firm conclude there's a difference in household incomes for subscribers to the 4 service providers? So now to set up the null and alternative hypotheses, the null hypothesis is just that all 4 of the population means are equal. And then the alternative hypothesis isn't that none of the 4 are equal, it's just that at least 2 of the means differ. So, and then also we're told to test this at the 5% or 0.05 significance level. So once again, this is based on an F critical value, which is based on your significance level, and then 2 different degrees of freedom. D1, or your degree freedom of number 1, is the number of populations subtract out 1. So in this case, the number of populations sampled were 4. So D1 would just be 4 subtract 1, or 3. And then D2 is the sum of all the samples subtract out the number of populations. So the sum of all the samples, again, would be 4 samples of 28, so 4 times 28. Then subtract out the number of populations, again 4. And that comes out to be 108. So now what you want to do is go online and look up the F critical value relating to a D1 of 3, a D2 of 108, and a significance level of 0.05, and you should get an F critical value of 2.6887. Now once again, step number 4 is figure out the F test statistic. We already calculated that's 15.23. Now step number 5 is to make the decision finally. Since our F test statistic is greater than our F critical value, we can reject the null and accept the alternative. So at the 5% significance level, there is evidence to suggest that at least two of the population means are different.